So let's start with gradient descent. This is a picture of gradient descent. Really, gradient descent, we're trying to optimize on W to minimize some form of cost function, and we're just iterating by, modifying W with something that is proportional to the gradient of the loss on W. This works well, but if we're not well conditioned, then the problem is the gradient is not pointing in the direction of the minimum, even in the case of a simple quadratic function. And then things start going bad, and you get these kind of oscillating behaviors, or you need to decrease the step size a lot, and then you get very, very slow convergence. And really the reason is because if you look at the local gradient, I can use pointers or I can move around. If you look at, well, they're both as bad, using pointers or moving around. If you look at the local gradient, right, it's not in the direction of the minimum. And so you're just oscillating. And the solution is well known. You do something that is second order. So basically you look at the curvature, and with the curvature you can correct your gradient. This works extremely well if you're in batch settings, and there are all kind of very good ways of approximating the Hessian. In online settings, it's a much, much, much more difficult problem. As far as I'm concerned, it's not solved. At least it's not solved in a very robust way. And you should ask people like Nicolas Leroux.
But momentum gives you
right.
Solution.
Exactly. Momentum gives you a lot of solution. This trivial problem would be solved by momentum. I'm just giving the intuition, right? I'm not claiming to do state of the art on gradient descent. But this, as far as I'm concerned, this is an important problem. Stochastic gradient descent, the idea is your cost function is the sum of many identical cost functions. So you can think of it as the expectation on a random distribution of an individual cost function. And then if you rewrite the gradient descent in terms of expectation, then the idea being that you are going to use a cheap estimate of this expectation. And I will call this our first butchering. You're basically, if you subsample the sum, you get an unbiased estimate with more variance, and this variance will be a problem. But then you can still get convergence, and something that's crucial is that you need to decrease the step sizes in a certain way. So other disclaimer, I'll be talking about optimization, so minimizing functions. I will not be talking about generalization, and there might be differences. You, especially with complicated objects like neural nets, you might not want, you want to be careful about how you optimize. This is not what I'll be talking about today. Okay? So this is gradient descent. People have pushed this much, much further, and this is the workhorse of deep learning these days. So it, has challenges. Well-known one is vanishing gradients. So in recursive neural networks, but also in very deep networks. The idea being that you're propagating the information across many, 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 many layers, and if those layers are not well conditioned, then information just vanishes. This is a conditioning problem, right? It means that if you have a very, very deep net, the modification that you need to do at the bottom of your deep net, at the weights of your entrance layer, may have a very different scale than the one that you need to do at the output to have the same delta on the output, okay? So extremely different scalings. Extremely different scalings means conditioning problems. Extremely different scaling is what we have here. We have two variables that have very different scalings, okay? So this is a conditioning problem. People have looked at it as a conditioning problem and have contributed very interesting stuff that I will not talk about. Another advance that I claim is related is batch norm. I like the view that batch norm somewhat controls conditioning, and there has been some conceptual results that show this. And the way I like to think about it is I like to think about a deep linear network. A deep linear network is something I understand better than a deep nonlinear network. So basically, I've got a product of many matrices. And the problem is that those matrices, I'll get the same exact output if one goes very big and the other one goes very small. Okay, so I've got this instability, and this instability, if it happens, will create a bad conditioning. So if one layer has become huge and another layer has become tiny, it means I don't have the same natural scales on both layers. So I have a conditioning problem. And batch norm somewhat addresses this.